Thank you. So welcome to my talk, Knee Deep in Microservices. This talk is, as Spinny said, going to be about microservices, Cloudnative, and hell demons from Doom. I'm a senior engineer and consultant at Amsterdam-based consultancy Container Solutions. And I'm a big fan of the classic FPS video game Doom. And while playing Doom, I made some realizations how similar it is to running microservices in production or building them. So Doom is a game about scientists on Mars opening a portal to hell to channel clean energy from hell to Earth. Well, as you can expect, that did not work out too well, and the demons overran the facility with only the green armored Doom Marine standing between them and humanity. Microservices are a very popular architectural style today because big companies like Netflix and Google basically had to architect their applications this way because of their scale. And people in smaller companies are looking at this architectural style and wondering whether we should also use it, or going heads in and not really caring about the risks or realizing them. So not everybody is deploying a large number of components by a large number of teams and having millions and millions or billions of requests per second on their servers. But is it really, is it too big a risk, or do the benefits outweigh the risks today? What are the benefits of microservices? And what are the demons you might unleash upon yourself if you go that way? First of all, microservices are a great architecture to utilize elastic cloud resources. So you'll be able to scale your application more efficiently. If you have several teams delivering your software, or even sometimes it can work with one team, your development velocity can increase because you are delivering components independently. Thus, after an initial increase or decrease in velocity, you can later, when your application's complexity increases, you can deploy faster. Resilience of the application to failures increases because you can run it over several geographical locations, several data centers, and today's public cloud providers make that easy for you. But you do need an architecture that will support that. Finally, cost optimization. If you have components that have very different performance and resource usage characteristics, with a microservice architecture, you will be able to scale them independently and thus utilize cloud resources better. So, when I'm talking, I want to clarify a bit what I mean by microservices. It's a very vague term used in lots of different ways over the years. What I mean by them and during this talk is separate code repositories for separate modules or separate components of your application that are packaged as independent artifacts that then are deployed in a way that those artifacts are not, for example, lumped together into a single virtual machine, but are managed by the production platform as independent components. All of this diagram could be modified in lots of different ways for practical reasons. So you might want to have a monorepo for your code, but somehow build different artifacts. Or what most of the time happens with, or many times happens with monolithic applications, the code might even be separate, but it's lumped together into one big artifact. Or everything is separate, but then it's installed on a VM and run everything is run together. So these are all valid options. There is not a right way to do microservices. I'm not trying to imply that, especially with legacy applications, evolutionary reasons, how things evolved with an application. Those are all valid approaches. But now I want to show the benefits of a pure microservice architecture, especially in relation with cloud-native technologies. So what are the demons that you will be unleashing when going microservices? Oh yeah, as a slide about being prepared. So even though these scientists failed horribly, they did actually have a status message saying demonic invasion in progress. That's very cool. So your first step to being prepared is sitting on this talk. So first of all, you will need to package your application. You need a technology that actually allows you to package applications in a uniform way, in a way that can be delivered to production unchanged. So you don't produce something that then is packaged by the ops team into something else and then is deployed in a different way onto a production system. You also need a technology that allows you to deploy every artifact you have in a uniform way, because otherwise the complexity will make your production environment into a very heterogeneous environment where all kinds of different artifacts are deployed differently. So in the end, there will be a pushback from the operations team to just keep it simple and let's just make everything Java, for example. Local development will be a problem with microservices. When you run one, your IDE and everything is made to run an application, maybe two, you make your configurations and everything. If you have 10, 15, 20 of them, then it becomes much, much harder to run your application on your local development environment. And that people sometimes don't even realize, but slows down the whole team velocity by a lot because you have a hard time testing features or your changes in isolation. Observability. Also, just as local development was always something to solve, but with microservices it becomes harder. Monitoring also becomes much more crucial and different and more important than with a monolithic architecture. Self-healing is something you will need up to at least some degree, because if you're running hundreds of small services in production, you cannot have the sysadmin guy go and restart something when it fails. And finally, your biggest problem will probably be organizational silos, at least for lots of companies. Actually, funnily, for some companies, it's not a problem because they just don't have an ops team, for example. And, well, they have other problems then, but at least the infighting between the ops and development teams does not happen. So basically, operations wants stability, doesn't want things to change because that's how they manage to keep things running. Developers want to push new features. Suddenly developers decide that instead of 3 artifacts, they are going to break the application down into 20 or 50. And all that stuff that has previously been contained inside the application suddenly becomes visible for operations and starts communicating over the network. So it becomes way more complex for them. For this, you need good cooperations between the operations and the development teams to handle that newborn complexity. But, well, for all these scary demons, you have cloud-native weapons to battle them. Cloud-native technologies have become quite popular in the last 2 years. They bring completely new ways to handle these challenges of microservices. I'll show how. They don't solve all the problems. So I'm not trying to imply here that you just use cloud-native technologies and microservices just become super easy and everybody should do it. They don't help with your overhead of developing independent components. So on the code side, there is not that much that has happened in the last few years. At least I didn't see it. But on the right side and the middle, the artifacts, we have now a good packaging format and we have a new way of deploying stuff. Docker is the technology that lets you package your applications, slice up your virtual machines, and deliver to production a range of different technologies in a uniform way that the operations team can understand, can handle, can run, and the development team can actually also utilize in their development process. Docker Compose can help with local development because Docker containers, the whole technology around Docker is a new kind of better way of virtualizing, or at least a lighter way of virtualizing things. You can actually have that virtualization on your laptop using either Docker Compose or other tools like Minikube or Minimesos, which actually even run a more realistic cluster on your machine. And thus you have a nice and easy way to actually run several components together on your laptop until the resources on your laptop allow it. So that's also great. And then the big guns. This is the, what you see up there is the BFG, the big fucking gun from Doom. It's the most powerful one, as the orchestrators are the most powerful tools we have to manage our production environments. Container orchestrators take a set of virtual machines and utilize them to run your containers over them. This doesn't sound all that revolutionary. It's a nice thing because once you package containers, you will want to run them somewhere, and this orchestrator takes care of that. But why this has enabled a very different way of managing our applications is because the orchestrator is looking at your application at a much higher level of abstraction than previous tools. So when you were installing VMs using Puppet, your level of abstraction is pretty much files in the operating system and services and stuff, and not applications. With containers, this level of abstraction moves higher, and a container orchestrator actually understands that your 3 front-end containers that you see there distributed over 2 different nodes belong to the same application component, and thus can provide load balancing over them, or scaling them up and down, or service discovery, with even a DNS server that you can just address front-end, and your traffic gets routed to the right container. So with this, things become quite different, which can be seen how monitoring solutions. So monitoring solutions are a good example of how things evolved. There is a short list of some of the cloud-native monitoring solutions that have that can now monitor containers in production that are running on a container orchestration system. It's very interesting to see that a year or 2 ago, monitoring solutions were really much trying to catch up to monitoring containers, because containers have a much shorter lifespan than VMs, and also you cannot just install agents and stuff into the container, because container is designed to just run one single application process. So the way these monitoring solutions were working before was not tenable for the container world. But what was fortunate for these monitoring solutions, and why they actually managed to even improve compared to the previous state, was that the container orchestrator, the master, actually has a global view of everything that's happening in the cluster. It has, actually all the container orchestrators have an API that you can query and get this global state. And as I said, it's a close to application level abstraction. So that means that in my example here, I have the co-scale monitoring tool showing me CPU time of my services. And those services up there, and now this has a laser. Okay, so these services up here, in the olden days, I would have had to configure what a service means. I would have to tell somehow the monitoring solution. Now I no longer have to do that. The monitoring solution can just ask the Kubernetes API, grab all the services, ask what containers are behind those services, monitor those containers and aggregate the results into this graph here. Or it can monitor how many containers actually make up the service. So you can see here is a spike in the CPU usage, and you can see a spike in the number of containers, so actually the service is scaling up. Unfortunately here the labels are a bit messed up. So this shows very nicely how in the cloud native world the concept of microservices is becoming easier to manage in production. Next is continuous integration. It's something all these tools have caught up with containers in a way that they can build containers, they can talk to orchestrators. Usually not in a very nice way. There is still work to do in this area, but you can use your tools that you know and like to build and deploy containers. So, what's going to be the path your company will have to take when you decide for a microservices cloud native adoption? You will need to implement independent delivery of components to leverage your microservice architecture. You will need to be able to manage these cloud-native environments. You will have to have a bit updated CI/CD chain in case you already had a relatively good one. You will have to be able to manage production workloads efficiently, do training of your people in these technologies, and you have to do good DevOps. Oh, monitoring, yes. You have to do good DevOps and do the cloud native monitoring. So I will use this example from one of our customers that we work together with them to put their application in production on a Kubernetes cluster in the Google Container Engine. It's a relatively simple application. It's not an example of 1,000 microservices, but it illustrates my point on why it's not just cloud-native technologies helping you to run microservices in production, but also the microservices architecture is very, I'm not sure if it's absolutely necessary, but at least it's very well fitting with what you can do in the cloud using container orchestrators. So what happened here was this company decided to migrate away from their legacy application, which was a classic .NET web application with a database behind it, to a whole new stack, actually insource it from a outsourcing company, and build everything on top of Node.js and Elasticsearch. And what they did was build an exporter from the old database to push the data that was still updated to RabbitMQ and import it through the new application into the new database. This was necessary because the migration happened step by step. So the new application was slowly catching up with features to the old application. And until that actually was finished, they had to build a proxy that actually proxies requests for features that are not yet finished to the new application. And they built this by creating an admin component, a front-end component, and lumping 3 back-end components together into a kind of a monolith. So the problem we encountered when we were working together with them and putting this application into production was, for example, the importer component needed to be scaled together with the backend. So what happened when load hit the application, that the importer scaled up and started importing messages from the old database or the data from the old database actually faster, while the application was getting extra load from the front end. That was a very bad situation there. The proxy component, while actually that one could be scaled with the backend, and even it kind of makes sense because they are under load at the same time, couldn't be monitored separately from the backend. So when we had a high CPU usage or overflowing memory, there was no way to tell whether it's the importer, the proxy, or the backend that is at fault. And with this Cloudnative, as I saw, the monitoring solutions and with the orchestrators, actually, you get a very deep view into your system if you actually split it up into separate containers running separate processes. So, your next step will be independent delivery of components. If you want to really leverage that you have a microservice architecture, don't deploy all of them together. It might be a good intermediate step, but try to move towards separate source code repos, separate artifacts, and don't share code between them. The common library that contains 80% of the code is a very bad pattern, because then you just cannot deploy things independently, even though it might look like that until you actually change something in the common library that will break something in a completely different service. And application components should own their own database, again, to be able to be deployed independently. How we did this? With this application, we packaged in Kubernetes every service as a Kubernetes deployment that can be scaled independently. They are grouped together into a service and auto-scaled using a horizontal pod autoscaler. So this is a super simple diagram. Everything is very uniform. Everything is a container, everything is a deployment, everything is a service that load balances between those containers, and everything has an HPA, and horizontal pod autoscaler, it's called in Kubernetes. It's a component or a piece of configuration that actually scales up the application up and down. And their database is a managed database at Elastic. So that's also a very important tool you can use in a cloud architecture. Just let somebody else handle a database, the queue, or your Kubernetes cluster. Especially for smaller companies, that's a very good idea to do. Managing environments, you have to have environments that are cheap, disposable, and versioned to have a very stable, predictable delivery. In Kubernetes, so I keep using that as an example. You have namespaces for this. In namespaces, you can isolate your containers, deploy the same application several times, while it's in every namespace, it feels like it's the only thing on the cluster, and you can create these namespaces are they practically don't cost anything. So the creation of a new environment took us as long as the slowest container to start up, which means pretty much seconds. Production workloads. You will need to do autoscaling. I mentioned the horizontal pod autoscalers before. Other container orchestration systems have different ways to do this. You will have to be fine-tuning resource limits and reservations on your cluster. I think this is the most, at least for me, when working with Kubernetes clusters, this was the most surprising thing that was hard to do, was actually deciding how much CPU should a service have reserved and how much it can use at maximum. With lots of different environments running on the same cluster and sharing resources, you have to be very careful about this. If you give too much to a container, too high reservation, then you will be running lots of virtual machines to accommodate all those containers with all those that are hungry for CPU, and maybe not doing anything, because when you reserve a CPU to a container, it's reserved and the container might not be doing anything and it will still be occupying the CPU. Of course, autoscaling mitigates that, but it's an effort to get this right. And if you give it too little reservation, then other containers can starve it. Continuous delivery. This part doesn't differ that much, except from how you might have been doing it before. It just becomes even more important. You need to make sure that whatever build tool you're using supports Docker. Most of the good ones support it now. How to push artifacts to environments, that's something you'll need to figure out. You will have some new container orchestrator. Your new way of deployment is talking to the API of the container orchestrator. So you will have to have a way to do that. Actually, these days, the CI/CD tools mostly let you just script it pretty much, which is not very hard to do. It would be nicer if there would be deeper integrations with the orchestrators. And an important point about DevOps, the Ops team creates the tooling for the continuous delivery. They don't take the artifacts from the development team and put them into production, because if that's happening, then there is no scalability in the number of services, because there is just no way the Ops team will understand every new service that needs to be deployed. Your operations team will have to understand container orchestrators, debug them, tie them together with monitoring and log aggregation solutions, while your development team needs to also be confident users of the platform. This is very important. We found that when developers don't have a sufficient deep knowledge of how things work, and they don't need to understand how Kubernetes internals work, but they need to understand the concepts and how to be a proficient user of it, then if that doesn't happen, they don't like to touch it, and the whole DevOps experience suffers because they will be pushing more and more onto the Ops team. And the monitoring, again, I already showed it, but now from a DevOps perspective, again, the Ops team delivers the tools. You might need inter-service debugging, so you will need inter-service debugging, so a log aggregation solution will absolutely be necessary. Put in some correlation IDs so you can actually find what happened to a request over different services that were all involved in servicing it. That will be probably work. We see usually that companies don't have that good monitoring and survive with it pretty well with a monolithic architecture. My guess is it's because of stack traces, mostly because they carry a lot of information to find out how a request went inside the application. But you lose that when you have services that communicate over a network. So you'll have to actually aggregate the logging from several services and then make sure they don't log too much, because then it's again hard to find out what's the important stuff. And finally, DevOps. DevOps will be an absolute necessity. And you might need an Ops team to develop the tooling, or you go to some completely managed solutions which are out there, like we did with this customer of ours. They went to Google Container Engine, which is a managed Kubernetes, used the managed monitoring solutions in Google called Stackdriver, used the managed database, and still they ended up with one ops guy having to service things. So make sure, and if you already have an ops team in place, make sure they are not deploying applications, but they are developing the tooling that the developers then use to deploy the applications. And the environment should also be the developer's responsibility. The operations team shouldn't be like keeping up the test environment up and running somehow. Yeah, so the ideal view of this system would be this: all components separated and running in the orchestrator. So the Doom Marine traveled to hell to defeat the demons there, and succeeded, only to see the demons still getting to Earth, where he had to go and defeat them again to finally save humanity. It's gonna be a rough ride, but don't forget your Cloudnative weapons and don't be afraid of the demons. Thank you.